Let's begin by introducing the key terminology, RDHx, door heat exchanger. This component is the essential partner for an RPU. It's a large radiator that mounts to the back of a server rack. Hot coolant from the RPU flows through it, and fans dissipate the heat directly into the surrounding air. This creates a liquid-to-air system. The main advantage is that this setup can be deployed in a traditional air-cooled data center without needing extensive plumbing. CDU, Coolant Distribution Unit. This is the all-in-one solution. It's a smart pump that circulates coolant to absorb heat from IT equipment. Then, using an internal heat exchanger, it transfers that heat to the building's main water supply. This is a liquid-to-liquid handoff. CDUs can be installed inside a rack or as larger standalone units for multiple racks. RPU, Reservoir and Pumping Unit. This is a simpler unit that only does one job, pumping coolant. It circulates the liquid to absorb heat, but does not have a heat exchanger to connect to the facility's water. TCS, Technology Cooling System. This refers to the IT-focused loop. It's the entire closed circuit of coolant that flows from the CDU RPU through the servers to pick up their heat and back again. Its only job is to cool the technology. FWS, Facilities Water Systems. This refers to the building level loop. It's the main infrastructure that takes the heat from a CDU and carries it out of the building. Alright, let's talk about the most widespread application for a rear door heat exchanger. Simply put, the solution is designed to replace the standard rear door of an IT rack. The core objective is to use the facility's provided coolant to make the entire rack, quote, thermally neutral. What thermally neutral means is that the air exiting the rack is at basically the same temperature as the cool air it took in. This way, the rack doesn't add any heat load to the room. The workflow is as follows. The IT hardware inside is air-cooled, so it exhausts hot air. As this hot air passes through the special rear door, the coolant circulating inside the door absorbs the heat, returning cool air to the data center. Now, these heat exchangers come in two primary types, passive and active. The active solution is the key one to note, as it has integrated fans. These fans help drive airflow, which ensures you get the required amount of cooling. They also minimize the back pressure on the IT equipment's own fans, making them work more efficiently. The passive solution, on the other hand, has no fans and relies entirely on the airflow from the servers. Depending on the requirements, a passive unit may or may not come with integrated sensors for monitoring. Now let's move on to the next evolution, the liquid-cooled hybrid solution. This approach is a direct extension of the traditional door heat exchanger we just discussed. The key addition is that we now introduce direct liquid cooling for specific IT hardware components inside the rack. So how does this work? We leverage the fact that we already have facility coolant available at the rack for the door. We tap into that supply to also cool high-power components, like CPUs and GPUs, using dedicated liquid cooling hardware like cold plates and manifolds. For more precise control of the coolant going to those components, a CDU may also be incorporated into the system. It's important to understand that in this hybrid model, the rear door heat exchanger is performing two distinct functions. It continues its traditional role of capturing heat from the exhaust air to keep the rack thermally neutral. At the same time, it serves as the coolant source for the direct liquid cooling happening inside the IT chassis. The primary benefit here is that this dual approach can enable significantly higher component and overall rack power densities. Now, a critical design consideration is the door itself. While it can still be a passive or active design, it must be selected very carefully. Its internal circuitry and flow rate must be sufficient to meet the cooling demands of both the air it's cooling and the liquid-cooled components it's supplying. And as a final technical note, if a two-phase coolant were to be used, the system would require appropriate design modifications to accommodate that. Finally, let's explore a third approach, the air-assisted or coolant-to-air solution. You can think of this as the complete opposite of the traditional model we started with. Instead of using liquid to cool the air, this system uses air to cool a liquid loop. Here's the process. An internal, closed liquid loop cools the hottest IT components directly, using hardware like cold plates, manifolds, and a CDU. This loop is extremely efficient at pulling intense heat from CPUs and GPUs. That hot liquid is then pumped to the rear door heat exchanger. The RDHx's job is to reject this heat into the facility air, often using the existing exhaust air from the IT equipment to facilitate the heat transfer. This leads to a key takeaway. From the data center facility's perspective, this rack is considered 100% air-cooled. The building's infrastructure only needs to manage the hot air exhausted from the rack, not a separate liquid supply. This is what allows you to get the high-performance benefits of direct liquid cooling in a facility that was only designed for air cooling. A direct result of this design is that the coolant flowing to the cold plates will be at a temperature above the ambient room air. As with our other solutions, the RDHx can be either passive or active. The selection is based on the server fan's capability and the total cooling capacity required in kilowatts. Lastly, there's a practical design point to consider: the routing of the tubes to the door. The hinges must be placed on the side that allows the door to open and close freely without putting stress on the coolant tubes over time. Next, let's discuss the required physical dimensions for the door heat exchanger. These guidelines are critical for ensuring compatibility, particularly with open rack architectures. There are two main principles. First, the door's design must be compatible with the open rack standard. Second, the installation process should not impact the standard rack-to-rack spacing or pitch and shouldn't require any extra mounting components. Let's break down the specific guidance for both active and passive doors, looking at width, height, and depth. For the width, the rule is that the entire RDHx assembly must fit within the primary structure of the open rack. This includes the heat exchanger core itself, its housing, and any adapter frame used for mounting. Similarly, for the height, the main body of the door must be within the rack's primary frame. This measurement does not include components that touch the floor, like casters or leveling feet. The only parts permitted to extend beyond this frame are coolant connections and the interfaces for active doors, such as power and communication lines. Finally, let's cover depth. The maximum preferred depth is 1 foot, or 305 millimeters, including the mounting frame. Now, this is a strong guideline, but it can be flexible. This requirement may be overlooked as long as two critical conditions are met. It must not violate the required aisle spacing, and the door must still be able to open at least 90 degrees. Any such exception must be formally agreed upon between the end user and the solution provider. Let's review the door heat exchanger's impact on the data center layout and operations. The fundamental principle is that the solution must integrate seamlessly without disrupting the pre-existing environment. First, regarding serviceability, the RDHx must be removable and mounted on a hinge. This is a critical requirement to ensure quick and easy access to the rear of the rack for servicing components like fans, power bus bars, and manifolds. Next, there are two major physical constraints to consider. The first is weight and floor loading. When the door is mounted and filled with coolant, the total combined weight of the entire rack must not exceed specific limits. For Open Rack version 2, that limit is 1,400 kilograms, and for Open Rack version 3, it is 1,600 kilograms. To verify this, solution providers must supply both the door's dry weight and its internal fluid volume. This allows data center engineers to calculate the final weight based on the specific coolant being used and confirm it meets the facility's floor loading limitations. Furthermore, the weight of the door assembly itself, when filled, must be less than 150 kilograms, with a preferred weight of 100 kilograms or less. The second major constraint is aisle spacing. To ensure full functionality, a minimum aisle spacing of 3.94 feet or 1,200 millimeters is required between rack faces. This clearance is necessary to permit the hinged door to open a full 90 degrees without interfering with adjacent racks or those across the aisle. Adhering to these guidelines ensures the solution is not only thermally efficient, but also operationally practical. Now let's discuss the physical interfaces and connections for the door heat exchanger. The required connections will depend on whether it is a passive or an active variant. We can break this down into 4 categories: coolant, service, electrical, and communication. First, coolant connections. For installation flexibility, the system must allow for coolant pipes to be connected at either the top or the bottom of the door. The recommended pipe termination size is a 1-inch internal diameter, with the capacity to accommodate up to 1.5 inches. Importantly, there should only be 2 connections to the facility coolant: one supply for cold coolant and one return for the hot coolant. Second, service connections. To facilitate maintenance, such as draining the system or bleeding air, dedicated service ports should be included at both the top and bottom of the unit. The next 2 categories apply specifically to active doors. For electrical connections, the integrated fans require power. The design should offer options for either 110 or 230-volt AC supply, using standard C14 or C20 connectors. 2 key recommendations are that the door should be powered by the IT rack it is mounted on, and that it should support A/B power redundancy. DC power is also an option, supplied directly from the open rack busbar. However, in that scenario, it is critical to ensure the rack's power shelves and busbar design can account for the additional load. Finally, for communication, the unit should support standard 485 rupees or RJ45 Ethernet ports. It must also be compatible with common data center protocols like Modbus, SNMP, and HTTP for a web interface. Similar to the power, the recommendation is to integrate the door's communication as part of the rack it is supporting.